In calculus, integration deals with summing up values of a function of a given range. And it is usually used in finding the area of irregular shapes. In fact, integration is simply the reverse of differentiation. And speaking of differentiation, let's look at that for a while. Now, consider a function y is equal to 2x squared plus 5. To obtain the gradient function, we differentiate that. So dy over dx is equal to 2 times 2 will give us 4, and then we reduce the power by 1, so we get 4x. The derivative of a constant is 0, and so dy over dx is equal to 4x. Now, consider this set of lines. Looking at them, they appear parallel. In truth, the lines are indeed parallel, and that's because they have the same gradient. If you compare the equations with the general equation of a straight line, y is equal to mx plus c. M in all cases is 3. In an event, if you differentiate all the functions, dy over dx will be equal to 3. So the only thing that differentiates them is the c, which is dy-intercept. Again, consider this set of curves. All of them have the general equation y is equal to x squared plus c, where c is dy-intercept. The gradient function for all of them is dy over dx equal to 2. They does form a family of curves with the same gradient function and only differ in the y-intercepts. Very well, now we look at reverse differentiation. Now, in differentiation, we obtain the gradient function from the equation of a curve. Given the gradient function, we can reverse the process and obtain the equation of the curve. This is called reverse differentiation or integration. Consider equation y is equal to x to power 4 plus 1. 1 is a constant and can actually be any number. In differentiation, dy over dx will be equal to, we multiply x by its power, so that we have 4x. And then we subtract 1 from the power. For minus 1 will be equal to 3. If we differentiate a constant, we get 0. And so dy over dx will be equal to 4x cubed. Now, suppose we are given this 4x cubed. We need to go back to the equation y is equal to x to power 4 plus 1. We simply reverse the two steps. So y will be equal to, the second step in differentiation was subtracting 1 from the power. And so the first step in integration will be adding 1 to the power. So we shall have 3 plus 1, which gives us 4. And so we shall have 4x to power 4. The first step in differentiation was multiplying x by its power. And so the last step in integration will be dividing x by its power. And so we shall have 4x to power 4 divided by 4, the new power. And so we shall have x raised to power 4. However, we had 1. How do we get it back? There is nowhere to know what number was there. But in any integration process, we always assume there was a constant. And so we add AC. This is called the constant of integration. Another example, dy over dx is equal to 6x squared. What will be y? We integrate 6x squared. And so y is equal to, add 1 to the power and we shall get 2 plus 1 is equal to 3. So we have 6x to power 3. And then we divide the whole function by the new power. 6x to power 3 divided by 3 will give us 2x to power 3. And then we add c. If it's a polynomial in x, we integrate each component separately. For example, dy over dx is equal to 4x to power 4 plus 3x squared minus 4x. To get y, we integrate that polynomial. So y is equal to 4x to power 4. If we integrate, we add 1 to 4, we get 5. And then we divide it whole by the new power 5. So we have 4x to power 5 over 5. Plus 3x squared, when we integrate, we add 1 to 2 and we get 3. We divide the whole of that by the new power 3. So we have 3x cubed over 3. Then 4x. X is raised to power 1. So we add 1 and we get 4x squared. And then we divide it by the new power 2. So we have 4x squared over 2 and then we add c. If we simplify that, we shall get 4 over 5x to power 5 plus x cubed minus 2x squared plus c. The example, dy over dx is equal to 7x to power 4 plus 2x cubed minus a 3x squared plus x. We integrate each of the components of that polynomial. 7x raised to power 4, if we integrate that, we shall get 7x raised to power 5 over 5. Plus 2x raised to power 3, if we integrate, we get 2x to power 4 over 4. Minus a third x squared, if we integrate, we shall get a third x to power 3, everything divided by 3. And then plus x raised to power 1, when we integrate, we get x squared over 2. And then we add c. We simplify that and we get 7 over 5x raised to power 5 plus 1 over 2x raised to power 4 minus 1 over 9x cubed plus 1 over 2x squared plus c. And finally, what if we had a constant? For example, dy over dx is equal to 4. 4 is the same as 4x raised to power 0. Remember, any number raised to power 0 is 1, and so to integrate, we add 0 plus 1 and we get 1. We divide by a fact and we get 4x over 1, and then we add c. And so that will give us y is equal to 4x plus c. Next, we look at integration notation. Now, this symbol is used to show that an integral is to be calculated. In general, this means that the integral is to be calculated with respect to x. So, if x simply means a function having x as the variables. For example, y is equal to 4x to power 4 plus 3x squared minus 4x. And because y is equal to 4x to power 4 plus 3x squared minus 4x, you can actually replace fx with y. But in almost every equation, we will have fx. If the variables were y, then we would have fy. And so this means the integral of 2x to power 4 with respect to x. This means integral of t cubed with respect to t. The function to be integrated is called the integrand. And the outcome is called the integral. In this case, 2x to power 4 and t cubed are the integrands. In differentiation, we see the derivative of. In integration, we see the integral of. And so if dy over dx is equal to a, then the integral of a with respect to x will be equal to y. For example, if y is equal to x to power 4 plus 5, then dy over dx will be equal to 4x cubed. And therefore, the integral for x raised to power 3 with respect to x will be equal to x to power 4 plus c, which is also equal to y. Let's take an example. Integrate each of the following. 1x squared minus 3x plus 1 and x plus 1 squared. In the solution for the first one, we write it in the conventional way. The integral of x squared minus 3x plus 1 with respect to x will be equal to a fad x cubed minus 3 over 2x squared plus x plus c. The second one, we expand fast. That will give us x squared plus 2x plus 1. So we find the integral of x squared plus 2x plus 1 with respect to x. That will give us a fad x cubed plus x squared plus x plus c. Excellent. Now we move to definite integrals. So far, when integrating, there has always been a constant left out. And for this reason, such integrals are said to be indefinite. With definite integrals, we integrate a function between 2 points, and so we can find the precise value of the integral, and there is no need to add any unknown value. In any event, the constants will cancel out. For example, the integral of x plus 3x squared with respect to x, but then we have a superscript 8 and a subscript 4 on the integration symbol. This means the integral of x plus 3x squared with respect to x between x is equal to 4 and x is equal to 8, where 4 is called the lower limit and 8 the upper limit. To work this out, we proceed as follows. We find the integral and then write the limits with the square bracket. So the integral of x plus 3x squared will be x squared over 2 plus x cubed plus c. We put the square bracket and add the limits. The upper and the lower limits are written like this to mean that they will be substituted in the expression in the square bracket. Next, we substitute the limits into the expression separately and then subtract the substituted functions, that is the upper substitution minus the lower substitution. So first, we substitute 8 for x in that expression. So we shall have 8x squared over 2 plus 8 cubed plus c in one square bracket minus the substitute the lower limit, for squared over 2 plus 4 cubed plus c. We work that out and we shall get 32 plus 512 plus c in one bracket minus 8 plus 64 plus c. We continue, we shall have 544 plus c minus 72 minus c. That will give us 472. You notice that the integration constants disappear with definite integrals, and so you don't have to write them. In general, the integral of fx with respect to x from x is equal to a to x is equal to b is equal to fb minus fa, where fb is the integral value at the upper limit, x is equal to b and fa is the integral value at the lower limit. X is equal to a. This expression is called a definite integral. It does not involve the constant of integration, and it gives us a definite value that is a number at the end of the calculation. Let's take a few examples. First one, evaluate the integral of 3x squared plus 4x plus 1 with respect to x from x is equal to 1 to x is equal to 5. So 1 is the lower limit and 5 the upper limit. We find the integral and write the limits in square brackets. So the integral of that will be x cubed plus 2x squared plus x in square bracket, and we put the limits. By now you know how to integrate. Then we substitute and subtract. So to get the integral value for the upper limit, we substitute 5 into the integral function. So 5 cubed plus 2x 5 squared plus 5 in 1 square bracket minus to get the integral value for the lower limit, we substitute 1 into the integral function. So 1 cubed plus 2x 1 squared plus 1. So we shall have 125 plus 50 plus 5 minus 1 plus 2 plus 1. That gives us 180 minus 4, and that gives us 176. A more complicated one. Evaluate the integral of 2x plus 3 root x with respect to x from x is equal to 4 to x is equal to 9. Now a solution. The square root of a number is the same as the number 2 power a half. So rewriting that, we shall get the integral of 2x plus 3x to power half with respect to x from x is equal to 4 to x is equal to 9. So that gives us x squared plus 2x raised to power 3 over 2 into the square bracket, and we put 9 and 4. Proceeding to get the integral value for the upper limit, we substitute 9. So we shall have 9 squared plus 2 times 9 raised to power 3 over 2 in 1 square bracket minus to get the integral value for the lower limit, we substitute x for 4. So we shall have 4 squared plus 2 times 4 raised to power 3 over 2 in that square bracket. That gives us 81 plus 54 minus 16 plus 16. That gives us 135 minus 32, giving us 103. Last example. Evaluate the integral of 5 plus 6 over x to power 4 with respect to x from x is equal to 1.2. To x is equal to 1.6. It looks complex, but a small flashback will keep us going. If you recall, in the reciprocals, 1 over x raised to power 4 is the same as x raised to power negative 4. And therefore 6 over x to power 4 can be written as 6x raised to power negative 4. So we rewrite that the integral of 5 plus 6x raised to power negative 4 with respect to x from x is equal to 1.2 to x is equal to 1.6. That will give us degrading that 5x minus 2x raised to power negative 3 in the square brackets, and then we put 1.6 and 1.2. To get the integral value for the upper limit, we substitute x for 1.6. So we shall have 5 times 1.6 minus 2 times 1.6 raised to power negative 3. Minus to get the integral value for the lower limit, we substitute in 1.2. So we have 5 times 1.2 minus 2 times 1.2 raised to power negative 3. Rearranging fat, we get 5 times 1.6 minus 1.6 raised to power negative 3 is the same as 1 of 1.6 raised to power 3. So we put that as 2 over 1.6 raised to power 3. Minus 5 times 1.2 minus, we do the same and we get 2 over 1.2 raised to power 3. So we shall have 8 minus 0.488 minus 6 minus 1.157. That gives us 7.512 minus 4.843, giving us 2.669. Next, we look at some applications of the integration process. One of them is the area under curves. Now we have already seen how to estimate areas under curves using the trapezium rule. We noted that the area calculated can be an underestimate or an overestimate. We also said that to increase the accuracy we use as many small trapezia as possible. That means the smaller the width of the trapezia, the more accurate the approximation. Now for a very small value of delta x, the trapezium can be approximately a rectangle with the same width delta x and height as the y-coordinate. Therefore the area of such a rectangle will be y times delta x. The total area bound by the curve from the line x is equal to a to x is equal to b is therefore the total sum of the areas of these small rectangles, each of area y delta x. Therefore the total area is equal to summation of y delta x from x is equal to a to x is equal to b. However, the width delta x of the rectangles have limits which are obtained when delta x approaches 0. The area the limits is written as the integral of y with respect to x from a to b, where the integral symbol means summation, and the x is the limiting value of delta x. Therefore the integral of y with respect to x from a to b is the total area under the curve from x is equal to a to x is equal to b. In general, the area under a curve between 2 points can be found by doing a definite integral between the 2 points. The area under such a curve between x is equal to a and x is equal to b is given by area is equal to the integral of fx with respect to x from x is equal to a to x is equal to b. Usually areas under curves take various dimensions depending on the function of the curve and the length to be worked out. Type 1 area which is entirely above the x-axis. Now if you look at this curve, y is equal to fx is entirely above the x-axis. In such cases we find the area by simply finding the integral. For example, find the area bound by this curve y is equal to x squared plus 2 the x-axis, the line x is equal to 1 and x is equal to 2. To find the area we simply find the integral value between the 2 points. So we have area is equal to the integral of x squared plus 2 with respect to x from x is equal to 1 to x is equal to 2. Proceeding to find the integral of x squared plus 2, that will be equal to a third x cubed plus 2x put in square bracket and then add the limits. One is the lower limit and 2 is the upper limit. Next, we substitute in the limits and find the difference between the integral value for the upper limit and the integral value for the lower limit. So we have a third times 2 cubed plus 2 times 2 in 1 square bracket minus substitute the lower limit a third times 1 cubed plus 2 times 1. That will give us 8 over 3 plus 4 minus a third plus 2. That gives us 6 2 over 3 minus 2 and a third, which gives us 4 and a third square units. That is the area under the curve from x is equal to 1 to x is equal to 2. Second type, type 2 area, which is entirely below the x-axis. Now in this case the integral gives a negative number, but since area cannot be a negative we often take the absolute value. In other words, we ignore the negative sign in the answer. Therefore area will be equal to the absolute value of the integral of fx with respect to x from x is equal to a to x is equal to b. For example, find the area bound by the curve y is equal to x squared minus 4. The x-axis and the lines x is equal to -1 and x is equal to -2. So area is equal to the absolute value for the integral of x squared minus 4 with respect to x from x is equal to -1 to x is equal to 2. If we integrate that, we get a third x cubed minus 4x putting square bracket and then put the limits 2 and -1. Then we need the absolute values. That gives us to get the definite integral. We substitute in the limits and then subtract the upper substitution minus the lower substitution. So we have a third times 2 cubed minus 4 times 2 in one bracket minus a third times minus 1 cubed minus 4 times minus 1. That gives us 8 over 3 minus 8 minus alpha plus 4. That gives us minus 5 and a third minus 3 and 2/3. That will give us a total of minus 9. We take the absolute value and get 9 square units. Type 3. Area that is partly above the x-axis and partly below the x-axis. In this case, we have to sum up the individual parts, remembering to take the absolute value for the section below the x-axis. That is from x is equal to a to x is equal to c. In other words, the integral is calculated in two parts. If you calculate directly from x is equal to a to x is equal to b in one bit, it would be wrong. So area is equal to the absolute integral value for fx with respect to x from a to c plus the integral of fx with respect to x from c. If you don't do this, the negative area will be subtracted from the positive area. For example, what is the area bound by the curve y is equal to x cubed? The x-axis, the line x, is equal to -2 and x is equal to 1. Now the first 3 over 2 is equal to -2 and x is equal to 0 is below the x-axis. And so we take an absolute value for its area. Total area will be equal to area 1 plus area 2. That is equal to the absolute integral value of x cubed with respect to x from -2 to 0 plus the integral of x cubed with respect to x from x is equal to 0. If x is equal to 0 to x is equal to 1, notice how the upper and the lower limits are structured. If we integrate that, we get a quarter x raised to power 4. We put in square brackets and then put the limits. 0 is the upper limit and -2 the lower limit for the absolute section below the x-axis. Then plus the area above the x-axis, we shall get a quarter x to power 4 and then the limits are from 0 to 1. Now to get the integral values for each section, we substitute the upper substitution minus the lower substitution. For the absolute section, we shall have the upper limit is 0. If we substitute in that integral, we shall have a quarter times 0 raised to power 4, which is basically 0. Minus substitute the lower limit a quarter times -2 raised to power 4. Then plus the area above the x-axis. We substitute the upper limit, which is 1, we have a quarter times 1 raised to power 4 minus the lower limit is 0. So that will give us 0 if we substitute. So we get the area below the x-axis will be 0 minus 4, but we need to take the absolute value plus the area above the x-axis will be a quarter minus 0. It gives us 4 plus a quarter, and it is equal to 4 and a quarter square units. Now so far in all the three types of questions we are working on the area bound by the curve and the x-axis. And so to say, we are effectively finding the area by horizontally adding the areas of the rectangles with width dx and heights y, which we find by substituting values of x into the function. And that's why the general area has been equal to the integral of fx with respect to x from a to b with absolute values where necessary. In certain other cases you may also be asked to find the area between the curve and the y-axis. To do this we integrate with respect to y. That means we find the area as the sum of rectangles with heights x, which is equal to fy and width dy. If we are given y is equal to fx, then we need to re-express this as x is equal to fy, and we need to sum from bottom to top. For example, find the area bound by the curve y is equal to root x minus 1 and y-axis. The line y is equal to 1 and y is equal to 5. In this case, we express x in terms of y. We have y is equal to root x minus 1. The square both sides and we end up with y squared is equal to x minus 1. If we rearrange that, x is equal to y squared plus 1. And so the area will be equal to the integral of y squared plus 1 with respect to y from y is equal to 1 to y is equal to 5. If we integrate that, we get a fat y cubed plus y, put the square brackets and then put the limits 1 and 5. To find the integral values we substitute in the upper limit and the lower limit into the integral and then subtract them. So we have a fat times 5 raised to power 3 plus 5 minus now the lower substitution of fat times 1 cubed plus 1. That gives us 125 over 3 plus 5 minus 1 and 1 over 3. That is equal to 46 and 2/3 minus 1 at a head, giving us 45 and a third square units. Next, area between two curves. Now consider two graphs y1 equal to f1x and y2 equal to f2x. We want to find the area between the two curves and the lines x is equal to a and x is equal to b. Think about it this way. The area between the curve y2 the x-axis and the lines x is equal to a and x is equal to b is given by area 2 equal to the integral of y2 with respect to x from a to b. Similarly, the area between the curve y1 the x-axis, the lines x is equal to a and x is equal to b will be given by area 1 equal to the integral of y1 with respect to x from a to b. Therefore the area between the two curves from a to b will be given by area 2 minus area 1, which is the integral of y2 with respect to x minus the integral of y1 with respect to x both from a to b. This can be achieved in one step by having area is equal to the integral of y2 minus y1 with respect to x from x is equal to a to x is equal to b. Another way of deriving this formula is this. Each typical rectangle has width delta x and height y2 minus y1. So its area is given by y2 minus y1 delta x. Adding all the typical rectangles from A to B, the area will be the summation of y2 minus y1 delta x from x is equal to A to x is equal to B. If delta x approaches 0, it becomes dx and we can integrate. And so area is equal to the integral of y2 minus y1 with respect to x from x is equal to A to x is equal to B. Second example. Find the area under the curves y is equal to x squared plus 5x and y is equal to 3 minus x squared between x is equal to negative 2 and x is equal to 0. From the graph, we see that y is equal to 3 minus x squared is above y is equal to x squared plus 5x in the region of interest. And so we use it as y2. Area will be equal to the integral of y2 minus y1 with respect to x from A to B. That is equal to the integral of 3x minus x squared plus 5x with respect to x from x is equal to negative 2 to x is equal to 0. If subtract those two functions, we end up with minus 2x squared minus 5x plus 3x. If we integrate that, we get minus 2 over 3x cubed minus 5 over 2x squared plus 3x square brackets and then put the limits. Then we substitute and subtract. Substituting the upper limit, we get 0. Minus substituting the lower limit, we will get minus 2 over 3 times minus 2 cubed minus 5 over 2 times minus 2 squared plus 3 times minus 2. That will give us 0 minus minus 10 and 2 times, which is equal to 10 and 2 times square units. Notice that some of the shaded area is above and some below the x-axis, but don't worry about taking the absolute value because the formula takes care of that automatically. Sometimes you may be given two intersecting cubes but not the coordinates at the points of intersection. In such cases, we solve the two equations simultaneously and find the points of intersection. For example, find the shaded area bounded by the cubes y is equal to x squared plus 5x and y is equal to 3 minus x squared. We know that area is equal to the integral of y2 minus y1 with respect to x from x is equal to A to x is equal to b, but first we need to find the values of A and b where the cubes are intersecting. This is simple. The points of intersection are where the two cubes are equal, so we quit the two functions x squared plus 5x is equal to 3 minus x squared. Solving that, we get 2x squared plus 5x minus 3 is equal to 0. Solve the quadratic equations. Two numbers, when we add we get 5. When we multiply we get minus 6. Those numbers are 6 and minus 1. Reciting fat, we get 2x squared plus 6x minus 3 is equal to 0. Factorizing, we get 2x into x plus 3 minus 1 into x plus 3. Proceeding to x minus 1 times x plus 3 is equal to 0. And if we solve that, x is equal to minus 3 and x is equal to 0.5. And so the cubes intersect at x is equal to minus 3 and x is equal to 0.5. So it is minus 3, P is 0.5. Having that, we can now proceed. Area will be equal to the integral of y2 minus y1 with respect to x from x is equal to minus 3. 2x is equal to 0.5. Proceeding, we subtract the 2. y2 will be 3 minus x squared. And y1 will be x squared plus 5x. We subtract and we get minus 2x squared minus 5x plus 3. And then we integrate that with respect to x from x is equal to minus 3 to x is equal to 0.5. If we do that, we shall get minus 2 over 3x to power 3 minus 5 over 2x squared plus 3x, putting square bracket and then put the limits. So we subtract the upper limit substitution minus the lower limit substitution. If we do that, we shall get 0.7917 minus 13.5, and that gives us 14.2917 square units. Finally, integration in kinematics. Now, a very useful application of calculus is displacement, velocity, and acceleration. Recall that in differentiation, we could find an expression for velocity if we differentiate the expression for displacement. Equally, we could find an expression for acceleration if we differentiate the expression for velocity. That is, velocity v is equal to ds over dt and acceleration a is equal to dv over dt, which is equal to d squared s over dt squared. Now, integration is the reverse of differentiation. It means that if we integrate an expression for acceleration, we get an expression for velocity. Integrate the expression for velocity and we get an expression for displacement. That is, v is equal to the integral of a with respect to time, and displacement is equal to the integral of velocity with respect to time. In fact, by doing a definite integral, we can find the exact displacement over a given time interval. For example, at Kcse from rest at s is equal to 3 meters from the origin and has an acceleration of a is equal to 2t plus 5 meters per second squared at time t. Find the velocity and displacement of the car at t equals to 4 seconds. V is equal to the integral of a with respect to time, and therefore v will be equal to the integral of 2t plus 5 with respect to t. That gives us t squared plus 5t plus c. Notice that this is an indefinite integration. When t is equal to 0, that is at rest, v is equal to 0, and if we substitute, we get c is equal to 0. So the expression for velocity as a function of time will be v is equal to t squared plus 5t meters per second. Therefore, when t is equal to 4, v will be equal to 4 squared plus 5 times 4, giving us 36 meters per second. Now, displacement. S displacement is equal to the integral of v with respect to time. S, in this case, we integrate the expression for velocity integral of t squared plus 5t with respect to t. That gives us a third t cubed plus 5 over 2t squared plus c. We add the constant. When t is equal to 0, s was 3 meters. Substituting that, we shall get c is equal to 3. So the expression for displacement as a function of time will be s is equal to a third t cubed plus 5 over 2t squared plus 3. Therefore at t is equal to 4, s will be equal to a third times 4 raised to power 3 plus 5 over 2 times 4 squared plus 3. That gives us 64.33 meters.